Hi folks, welcome back to Physics with Captain Rod, and welcome to Introduction to Vibration Part 2. So in Part 1 of this video I talked a little bit about how to derive the equation of motion for a simple harmonic system such as an oscillating spring here, an oscillating mass. I talked about what initial conditions were. I talked about coming up with the equation of motion for the system, writing out what's called the harmonic solution or the general solution to equations of this form. And I think we had just got done applying the condition that at t equals 0 the velocity has to be 0, which forces a to be 0 in this example, leaving our solution to look something like this for this specific problem. So I'm going to pick up on that right there, getting rid of this stuff that we're not going to need. All right, next step. So the next step here is to maybe go after the angular frequency. The angular frequency comes from the differential equation itself here. What we need to do is we need to substitute this solution into this equation, but you'll notice to do that we need this thing's second derivative here. So I'm going to take this guy and move it over here. If we time differentiate it, let's see, the derivative of cosine is minus sine, so we're going to minus c omega sine omega t. If we differentiate this again, we're going to get minus c omega squared cosine omega t. So now what we do is we're going to sub this and this into our equation of motion here. So that first term is going to read minus c, minus c omega squared cosine omega t for this. And what I'm doing is I'm subbing that right there. Plus, then we've got this term, k over m, times x, which we believe is c cosine omega t, equals 0. All right. Now what we have is an algebra problem, and we just need to figure out, what we can figure out from that. Well, for starters, you notice that you can divide this cosine term right out of there. We can't allow that to be 0 anyway. If we did, we'd be back to our trivial solution, x equals 0. The c can't be 0 because, again, we'd be back to our trivial solution. So the c and the cosine omega t get factored out. We're left with minus omega squared plus k over m equals 0. And that's the one we want right there. So from this guy right here, we can say, all right, the omega, the angular frequency, has to equal root k over m. And I can kind of update my solution here. So x is equal to some constant c times cosine of root k over m times t. All right, almost done. Last, this constant right here, the constant c. We don't need this stuff anymore. We can get the constant c from the initial conditions here. At t equals 0, x has to equal positive x sub o. I said positive because I imagine moving this thing to the right a distance x sub o. So if we just apply that condition, we're going to have x sub o equals c times 1 because the cosine of 0 is 1. So our constant c is whatever x sub o is. And here's our solution. Now I worked this out kind of generic without numbers. In theory, we'd have numerical values probably for this and all of this. You notice this is a cosine wave. If we were to graph it, x against t, and I'm just going to do a quick sketch. Does not have to be perfect at this point. So again, x against t. That cosine wave is looking something like this. And it would, do a little bit better job of that. Well, imagine a perfect cosine wave, etc. goes on forever. So this function would get as high as plus x sub o, as low as minus x sub o. And the very last thing I want to talk about how to calculate is what's called the frequency of the system. and the frequency is how many cycles per second it will oscillate through. And what I do to get the frequency is I just take note of one waveform here. If I were to go from here, I'm just going to look at one waveform from here to there. At that point on the curve, our cosine function will have cycled through 2 pi radians. So at that point in the curve right there, we can say that this root k over m times t would have to equal 2 pi. And then we can solve this for t. And you're going to get 2 pi over this guy. This t is a very special t. It's called the period. It's the time to complete one cycle. Now, the period is the time to complete one cycle. The frequency is the number of cycles per second. The relationship between the frequency and the period is the frequency is 1 over the period. So once you get your solution, just graph it. Take a look at one cycle. Basically set this equal to 2 pi. Solve for the t. You'll have the period. Invert it. There's your frequency. Right? So that's pretty much everything. I think that's right from the beginning to the very end, how to end up with the equation of motion, or I'm sorry, the position equation that describes the system and the frequency. And again, I kind of want to overview this in general. This was for just a mass spring system, but you can, these ideas really apply to any harmonic system, right? Including systems that involve rotation. You start by typically writing down the initial conditions of the problem, if you have them. Some problems will, some problems won't. Second, you derive the equation of motion for the system. You do that either by Newton's second law, net force equals ma, or by writing a work energy theorem and time differentiating it. Now, in either case, you have to watch out for other non-conservative forces. Some vibrational problems may have friction or damping or some sort of external force driving the system here. So this video is restricted to just standard harmonic problems that do not have external forces or damping. So the equations of motion should end up boiling down to something similar to this. Next, you write out the harmonic solution. In this case, that was x equals a sine omega t plus b cosine omega t. Now, for a rotational type of problem, your coordinate here may be an angle, and that's perfectly fine. Then you start going after the constants, a, omega, and b. The a and b you're going to get from the initial conditions of the problem. The omega you will get by subbing what your differential equation, by subbing your solution into the differential equation and solving for omega. Once you have your position function, you can find the period and frequency just like I just outlined. You can also derive equations for the velocity by hitting it with one time derivative, or the acceleration by hitting it with another time derivative. So that's a simple harmonic motion in a nutshell. Again, we're looking at, in this case, just the oscillating mass system. But again, these principles apply to also, to any type of harmonic system that does not have damping or some sort of driving force attached. And I think I'll save those cases for another video. Have a great day.